are live. Welcome everyone.
Hello there everyone and welcome to this week's episode of Dangerous Cosmology. I am your Commander Selfish Pie and I am here with your host Nightfall Zero, as well as Commander Shoba, otherwise known as the wonderful Dr. Sarah Bosman. As always, we have that Michael on technical.
Hello.
How are we all... Yep, there he is. How are we all doing this week, guys?
I'm fine, and you?
Oh, I'm doing
Great.
special. Cool.
Great. Nice intro indeed.
Why, thank you.
I couldn't have done better.
Oh, you
I'm having
could have.
Okay, yeah, today's episode is about dark matter and also dark energy and what this is all about. I think we should just head straight into the questions. We will be taking...
Yeah.
Oh, I've got to open up the YouTube and Twitch chat.
So we are indeed, as usual, both available on the Dangerous Cosmology channel on the Distant Radio server, or on the Fleetcom server in the Astronomy channel. We will be taking questions live. We have a few of them lined up. But of course, if you're listening in and you're hearing something that you would like discussed more, feel free to drop a line and we will see what we can do about that. As usual, we are also on YouTube and Twitch, so we're taking questions from there
as
too.
well. Yep.
Indeed.
I try to keep an eye on it, but I've only got so many screens.
So yeah, we decided to go for dark matter and dark energy because it seems to be one of the things that pop up during random discussions we've noticed. And I believe we touched on them briefly during one of our previous segments, but I don't think we went really deep into it. So we decided to clarify things once and for all. It was pointed out to me that since they are quite enigmatic in a sense, it happens very often that books or movies or even games sometimes misrepresent what we currently know about dark matter and dark energy. So hopefully tonight we will be able to shed some light, I guess, on these mysterious things. So, yeah, dark matter and dark energy. Shoba, can you... Let's just start with dark matter first, because they are two different things, although they have similarly ominous names. They are quite different, right? So let's start from dark matter. What exactly is the scientific definition of dark matter?
Dark matter is a type of mass that we have come to understand exists in the universe, but it doesn't interact with the electromagnetic force in any way, so it will never be visible. It would be better called invisible matter than dark matter. It is not dark in the sense of being black. It is dark in the sense of being mysterious. So it's out there, it's affecting how things turn with gravity, or how things behave in general, from very early times to very late times, but it doesn't interact with light, so we can't ever hope to take a direct picture of it. It's quite mysterious.
Unless we use something other than light.
Yes. Well, it's possible that it could interact with... Well, it does interact with gravity, so we can, for example, map quite precisely where it is in some cases and make very accurate maps of where the dark matter is by its gravitational effects. But we can't take pictures with light, because pictures are defined by light.
Yeah.
Okay, yeah, no, of course. So dark matter is this unknown substance that is everywhere, right? Or is it concentrated in some parts of the universe and completely absent in others? Is it some sort of mysterious particle that is just everywhere, we just can't see it? Or is it, centered in some specific regions?
Well, Unlike what people usually assume, we actually know a lot about dark matter. We know a lot of its properties, we know where it likes to live, and we know how it interacts with galaxies during their formation. So we kind of have very good models of where it ends up, and we can also confirm with observations of how it distorts gravity where it ends up. And we currently think it lives in big spheres around galaxies, depending on the type of galaxy. For example, a galaxy like the Milky Way will sit in the center of a big sphere, roughly a sphere of dark matter, extending probably 10 times more in size than normal matter. So it's distributed quite thinly. It likes to live in very big, puffy halos around galaxies. It's a bit more dense at the centers, but not dramatically so.
Okay, so most of it is in between galaxies.
Around galaxies, in what we call the circumgalactic medium.
Yeah, so there's not much of it inside galaxies.
And there is not much of it in between galaxies. The void between galaxies is much more void than the surroundings of galaxies. Inside of galaxies, it's a bit more dense than on the outskirts. It gets more and more dense towards the center, but it's not dramatic. There is quite a lot of dark matter inside the Milky Way, just not as much as people think. It's actually distributed in a very puffed up area outside too. But there is some. There is some in the solar system too. By all likelihood, there should be at least some.
There could be some in your room now, right?
Could be. Probably not
I'm
much.
sitting on some.
Maybe, and maybe not.
You're sitting on some dark matter.
Yeah, of course.
I mean, I would go to the toilet if I were you.
Okay.
But hey,
No, I won't go to
Sorry,
the
go
toilet
ahead.
because of this.
If we're talking about it being in our rooms unnoticed, it sounds like we're describing something similar to neutrinos. Is
Yes,
that
actually.
a possibility?
Yeah, actually, an extra neutrino, what we call a sterile neutrino, is one of the leading theories of what it would actually be. Just an extra particle that we can add to the model of particle physics that has the specific property of not interacting with photons in any way. It can still interact with other forces, maybe, like neutrinos do. And neutrinos are already extremely weak interactors. Like you said, neutrinos also pass through your body in enormous quantities every second. You would just never notice them because an interaction is so unlikely. So you take that to an extreme. If you had a neutrino where that interaction parameter was actually 0, that would make a very good dark matter candidate. And actually, particle physics doesn't cringe too much at that. Particle physics has a lot of variety in which interactions are allowed. It's not too crazy.
okay. So I mean, how did we come to discover this dark matter? I mean, if you can't, I understand gravity, so I guess that gravity was the way to discover it. But how was it actually done? Someone just noticed that gravity was weird, and they said, "Oh, it must be something there. I don't know what. Let's call it dark." Is that what happened?
Pretty much.
Pretty much. Pretty much. So I think first, historically, were clusters of galaxies. We measured the speed of individual galaxies that live in groups, and they were 10 times too high to still live in that group. If they were moving at that speed, it was way more than the escape velocity, 10 times more. So they would have escaped their group a long time ago. And yet they hadn't escaped, they were still in these huge groups of hundreds of galaxies without flying apart. So astronomers thought something must be holding them together, something really heavy. And back then, people were very keen on modifying gravity instead of just adding matter. That was the most obvious solution. We were really keen on that. But then, unfortunately, it turned out that the discrepancy is very different from one galaxy to the next, which really ruins that point. Because if you have to modify gravity, you modify it once. Why would one spiral galaxy spin 10 times too fast and one only spin 2 times too fast? Or some of them just spin at the correct speeds based on the stars that we see. So why would you have an enormous range of how wrong they are if you just want to modify gravity? And so when we started measuring things like that, having extra mass was really the only way.
So you just go with a process of exclusion. It can't be anything else, so it must be a new type of particle that we can't see.
Yes, and the intermediate step, like always in science, is we made a prediction before knowing what the outcome would be, and then we went out and tested it. So we predicted, for example, that dwarf galaxies should have more dark matter on average compared to their stars than spiral galaxies. So they should have more anomaly if you're not a spiral but you're a dwarf. And that was confirmed too. That's because of the way they form. You can have a big dark matter halo and that just fails. So we predicted that some dwarfs would be extremely anomalous. And this and many other predictions came true many, many times until modifying gravity almost died completely as a concept to fix it.
Okay, and
It was outrageous from the start, if I may say.
At the start, when it was just clusters,
And I
and
mean,
if
it
it
was
was wrong
outrageous.
by always the same
modifying
amount,
gravity.
you know.
I mean, modifying gravity was outrageous from the start. It's an idea.
Outrageous.
I can't get behind that.
It was a bit dubious because it works so well for our solar system. Like, exactly. It's not wrong by a factor of 10. So it had to be modifications that only affect gravity in some specific cases, like when things spin really slowly. Maybe then it breaks. People tried these ideas, like picking one part where it's wrong and finding a different theory of gravity that works only there. But then you break other parts, and it just didn't work. It never made verifiable predictions. So, bad luck.
Is not possible. Talking about the modification of gravity, you know how it's commonly described that general relativity isn't complete because it's not dynamic. That's what you've said in the past. Is it not possible that once we some way to make it dynamic, that might just be such a large chunk of general relativity that we're missing that it accounts for the apparent addition of hidden mass?
I mean, maybe in some cases, but what do you do when you have two galaxies that look exactly the same, right? They have the same number of stars in them, but one of them is spinning 20 times too fast and the other one's normal. Like, what's keeping one from flying apart and not the other one? If you go with GR, the amount of mass is the same. If there's no extra mass, so if you believe GR should be predictive, so you take what you see, you predict how it should move, but obviously that wouldn't be true unless there was another thing that was different between them. So it's observations like that will not go away. How can you have two almost identical galaxies with very different gravities happening?
I hate to be the bearer of bad news, but you're cutting out just a little bit.
Oh, so it wasn't just
sorry.
me.
all right. You mean cutting at the end and start of words?
No, during talking, just clicking noises I get.
Oh, maybe because I'm downloading. Wait,
Might be.
didn't think that was an issue. Okay, let's see if this works
Oh,
better for a bit.
oh dear.
Oh dear,
What?
what?
Now it's happening to me all over the place.
With me
Sorry,
also,
what?
or what?
What?
So now it's you, not us. Okay.
Can you guys? Is someone else listening in that can type if they're hearing us properly?
Yeah, please
That
tell
would-
us.
If there is any issue in the audio, better iron out it as soon as possible. So let us know.
Well, there haven't been any complaints yet, so I think we can just continue. for now.
Except one.
Yeah, selfish pies.
Yeah.
And it's just him being a selfish pie.
Anyway, what were you saying, Shoba?
What was I saying? I was talking about modifying gravity.
Yes.
Yes.
Sorry, that's my fault.
No, the problem is, even if you modify GR, ultimately you want the theory of gravity to be predictive. So based on what you see of the galaxy, you should be able to predict how it should move, because that's what gravity does. So you can never explain how you can have two galaxies that look the same. They look like they have the same number of stars, and yet one of them is experiencing very different gravity from the other. If it was just the mass that you see, and the same theory of GR for both, you should not have a difference still. And that will probably not go away, no matter how you modify gravity.
Okay.
Yeah, so the only option is to have something that we can't see for now.
And something that we're missing, right?
Yeah, there has to be a difference between those galaxies. We don't know what, but the most easy explanation and the one that's been confirmed with predictions is dark matter. We're not happy with it. Like, astronomers are trying very hard to find more about it in any way we can, really, or just detect it in any way we can. It's just really hard.
How much of it is there, though? I believe this is one of the questions that Michael asked.
Yeah, in a sense. It wasn't
Yeah,
exactly how much,
you
but
sent-
if you sum up dark matter, dark energy, regular matter, and regular energy, this still doesn't account for everything, for the entire mass of the universe, if I recall correctly. Isn't that right?
Yeah, well, we can answer the question after we talk about dark energy. Let's
Yeah.
take one step at a time. But no, then my question was, in terms of quantity of mass, how much dark energy is there compared to, not dark energy, not dark matter? Sorry, did I say energy or matter? I'm getting confused.
Matter.
Okay, how much dark matter is there compared to non-dark matter?
There is about 5 times more dark matter than normal matter. So that's the rough number, 5.4, I think.
So scientists don't really know shit.
Well, particle physics doesn't really have a problem with it, strangely. Because particles can opt in or out of some interactions with some forces. We have the strong force, the weak force, gravitational force, and the electromagnetic force. And we see particles that completely ignore one of the 4 fundamental forces. It happens. Like an electron will never feel the strong force. Quarks could look at an electron and be like, "Oh my God, how is he just ignoring this force that we all feel?" But the electron doesn't care. It just doesn't. And the fact that you can ignore some forces is already a feature of the model. So it's just a statement that most particles actually ignore the electromagnetic force, which is weird, but it's not completely insane.
Well, I mean, okay, they ignore it, but that doesn't mean that they don't exist, right?
We see them through their effect, gravitational, but also other
Exactly.
effects.
So you can't just say, "Oh, well, it doesn't really apply to us, so let's just ignore it." I mean, that's...
No, we don't ignore it. We try our best.
I know, your best is not enough. Try harder.
Sure, study physics, join us.
No, I have other things to do.
Shuffles away.
Yeah. Yeah, but anyway, no, okay, so there's a lot of dark matter, and there's a lot of stuff that we don't know what it is. We will go to the question about, theories and hypotheses of what this would be, but now let's switch briefly to dark energy, because dark energy is less talked about than dark matter. But sometimes there is confusion between those two terms, maybe because they're both dark.
Well, they're both named wrong.
Right. Well, you guys
wrong.
named them. So.
By that, do you mean they're both named wrong in the sense that they're both unknown?
They're named wrong because their names aren't very helpful to refer to what they actually are. The dark matter should really be invisible matter. And
Right, okay.
it should really be unknown force. That would be much better names. Invisible matter is actually a better name because that's what it is. We're quite sure that's what it is. It's matter that's invisible.
It doesn't sound cool, though.
Yeah, but at the time it was named, I guess it was more mysterious. Particle physics wasn't so advanced. We didn't know so much about it and its properties, where it is, and all that. But now it should be renamed. I think.
Okay, well,
Dark energy, though, is definitely not dark. Like, in any definition of the word dark, it's not dark, it's just mysterious. I wonder who came up with that name, actually.
dark
Some one
can
of
be
you
a
guys.
synonym of, well,
I wonder, let's look it up. Who came up with it?
you don't know?
Who had the terrible name of calling it dark
Are,
energy?
are you Googling?
Yeah, I'm Googling.
Really?
I don't know.
You're supposed to be the expert here.
I don't know the history of all of physics, you know?
Well, that's your problem.
So good, we get Google.
I only recently realised that there are people who are considered historians who they're exclusively historians in like space flight and the history of science. It's fantastic.
Oh yeah, that's a whole topic. History of science is something we all have as compulsory courses when you study physics, at least a bit of it. And people specialize in it. It's super cool.
Well, we can make a topic about that.
Dark energy, named that way by Michael Turner in 1998.
Okay, but okay, let's talk about it. What is it?
That's not too long ago. Dark energy has nothing to do with matter. It has nothing to do with things we can measure. Dark energy is a phenomenon. It's something we noticed, that on very large scales, galaxies, instead of attracting each other, start pushing each other apart. It is a motion that goes against gravity on very large scales, and the furthest away you are, the stronger it is. So we noticed this when we were mapping supernovae in distant galaxies, try to see basically how fast the universe was expanding. We already knew that the universe was expanding, so things further away were moving away from us very fast. But actually, not only is moving away from us very fast, it's getting faster and faster with distance, which makes absolutely no sense in the model of gravity that Einstein envisioned. If you start from a Big Bang, you sort of launch things in all directions, but eventually they'll slow down and fall back down. Like when you throw a ball up in the air, it slows down, it stops, and then it falls back down eventually. So that's what gravity should do. You throw all these things apart at the Big Bang, they'll keep moving away from each other for a while, but eventually slow down. But instead, they're accelerating. And we don't know why. We called it dark energy because it's the amount of energy it would take if it was being forced to happen. If something was pulling apart the galaxies, even though they want to attract, that amount of energy would be what we assign to dark energy. But really, it's a force or a phenomenon is a better name for it.
Dark force.
Okay.
The dark force.
Yeah.
Okay,
maybe
so
that wasn't used because of
so
Star
so
Wars.
it is
That's a better name.
so it is not a constant, right? Because I guess it changes depending on where you are. If you're far away, there's a lot of energy.
It kind of is a constant. It's just so you know with gravity we have the attractive constant that says that slows down by the square every time you increase the distance. So basically, if you take two things and they're attracting each other, you double their separation. Now they attract each other 4 times less. That's how attraction works. It's a constant. Dark energy is also a constant. If you take two things really far apart, they're going to repel each other. If you double their distance, they're going to repel each other twice more. It's also a constant, based on the separation of different objects.
Yeah, it is as much as a constant as gravity is.
Yes, it's as much of a constant as gravity is, exactly.
So dark energy is gravity.
It's repulsive gravity,
Anti-gravity.
Repulsive.
anti-gravity. On the very large scales, gravity reverses. That's one way of explaining dark energy.
That's still a hypothesis though, right?
Well, it's measured very accurately. It's not going anywhere, that's for sure.
No, but
It's being measured in detail, and it does seem to be constant in this sense. When you double the distance, it increases in strength.
so
Yeah?
I just had a very strange and likely untrue thought. But we're describing repulsive gravity, so my thought process is regular gravity, regular mass, repulsive gravity, negative mass? Question mark?
Yes, absolutely, actually. It's been a thing that's been flown around for a long time, and the
I am
idea
on
is
fire.
not negative mass as much as the vacuum. So in some leading theories, it's the vacuum. When you have enough void, the void tends to expand itself and gain onto regular matter. So in the spaces between galaxies, which are very empty, quantum mechanical effects are expanding the void, stretching space-time where it's sufficiently empty.
Wait a second, though. I mean, we know that space is expanding, right?
Yes, but yes.
So it's like when you're inflating a balloon. Okay, if you are on the surface of the balloon, as it gets inflated, you get farther and farther apart, and quicker, because the space between you and someone else on the balloon increases. The surface increases. So as the surface increases in surface, every time it, I'm trying to use proper words, but I can't.
No, I get what you
What
mean.
I'm trying to say is, if something is expanding, the bigger it gets, the quicker 2 points gets farther apart.
Yeah, absolutely.
So
that happens anyway, you're right.
So dark energy, obviously, the farther away two things are, say two galaxies, the farther they are moving away from each other for this reason, because
Just
the space
from
in between
expansion,
them,
yes.
the space in between them keeps expanding, and the space that itself that is created expands as a consequence. So
Yes. So that happens anyway, you're right. You're completely right. That's how expansion works. Something that's twice further away will move twice as fast as something that's closer. But on top of that, there is a big anomalous repulsion.
Michael, is it just me or is it happening again?
It's just you.
oh, that can't be us this time.
Yeah.
I'm gonna do an internet test. I'll be back in a minute.
Yeah, I don't think it's me, because I can hear all of you fine. So I think my internet works.
He is downloading Spaceborne. It's
Yeah,
probably
as always.
with belugas and stuff like that.
Youth these days.
Shameful.
Yeah. But okay, so you're saying in addition to this expansion.
Yes, in addition to this expansion, there is a repulsion. The expansion is accelerating over time instead of slowing down.
Yeah, but that's
Isn't
that's
that
what
exotic
would happen
matter?
anyway.
No. The expansion itself is accelerating. So it's expanding faster than it used to. The space between 2 points, instead of just doubling, it's more than double. So it's expanding faster than linear. It's on top.
Yeah, but couldn't that be just how expansion works?
Well, not really. That requires extra energy. It's like I said, when you throw a ball up, it might go up very far if you're very strong, and while it's going up, you get normal expansion. But it's not going to go up faster and faster, because it's still attracted to the ground. Just like the galaxies in the universe are still attracted to each other. They can start expanding more fast than they used to. So say us and, I don't know, the Perseus cluster, we're repelling each other stronger than we used to.
No. I understand that, but isn't this also true that gravity, two objects, the closer they are, the faster they attract each other?
Yes.
So, as if you throw a ball up in the air, when it is farther away from you, it is falling slower.
Yes.
It falls the fastest when it is closest to the ground.
Yep, definitely.
So following this logic, gravity works in that way exactly like dark energy does in the opposite. So the farther it is, the faster it goes. So it is basically mirrored.
Yes, once you go past a height, it starts accelerating up.
Yeah, it is basically mirrored. So you throw a ball up, there is a certain point in which it is in stable orbit. Well, not orbit, but there is a 0 point, after which it starts getting repelled faster and faster, as if at the other end there is gravity that is inverted. So it gets pulled faster and faster towards a hypothetical ground that is just upside down.
Almost, because the way it scales is not the same. So as I said earlier, with attraction, when you double the distance, you're less strong by a factor of 4. You're 4 times weaker if you're 2 times more further away. Dark energy doesn't work like that. It scales. So it repels 2 times more if you're twice as far apart. So in terms of physics, it's not exactly like that, but the principle is the same. There is a critical point, and beyond that, some other behavior takes over that accelerates it up at a constant rate.
But it is not exactly like gravity.
Not exactly.
Inverted.
No. It's actually less powerful.
Right. And again, we have no idea what it is.
We don't know what's causing it. Is it just a feature of gravity? Is it energy being pumped into the universe from the void? Or is it some other types of physics that we just don't know? Is it a feature of quantum gravity, the future theory that we don't have yet? And we don't know. It could be many things. It could be actual energy, or it could just be a feature. Is it a bug or a feature?
Right.
That's the question.
Right. Well, what you have explained kind of invalidates some of the questions that Michael asked, because you were also asking, Michael, if there is such a thing as a dark antimatter.
Yes.
But, I mean,
maybe.
Since dark matter is not something that is specified.
But we have good theories. Like we mentioned neutrinos earlier. Some flavors of neutrino can be their own antiparticle. So it's a bit cheating. But yeah, they could come in different flavors, why not? There could be more than one particle of dark matter, just a whole family of particles that don't interact with photons.
Yeah, no, what I'm saying is that you have antimatter, okay? And then you have this hypothetical anti-version of dark matter. But since we still don't know what it is because it's mysterious, we will still call all of it dark matter.
Yeah, it's still all dark matter.
So
invisible matter. It's all invisible.
So it doesn't matter if it's anti itself or not, since it's still mysterious and invisible. To us, it's all dark. It's all the same. It's all dark.
Well, it can have different names. For example, instead of just calling it a sterile neutrino, there are theories of what we call the dark sector. So a whole addition to a particle physics with dark particles, invisible particles that ignore photons. And the dark sector is a very cool name.
To what, like an invisible plane of existence?
Just extra particles that interact with each other, but not with us.
Yeah, that's what
Maybe
I'm
they
saying.
have their own photons.
That's what I'm saying, like an invisible parallel universe that we can't interact with.
It's not parallel, it's here.
Yeah, parallel in the sense of...
Yeah, I know what you mean.
You know,
it's out of
that's
phase.
what you... That's what you mean by parallel usually in sci-fi. It is there. It's like you open a tear on the fabric and you just step in a weird version of your own house.
Well, it wouldn't be like that for dark matter. But
I'm just, trying to depict how these things are usually portrayed in sci-fi.
So anti-dark matter in that sense, just many different types of dark matter particles all living happily together. Why not?
I don't know why not. I mean, are there actually papers written about this?
Yeah, I mean, it's part of what I do actually. I try to see how much structure there is in dark matter. Because depending on one of its properties, which we call misleadingly temperature, really it's the amount of energy. Depending on the amount of energy that dark matter possesses and how fast it's moving, it will forbid some structures from forming. And that's something we actually study. Like, what is the smallest structure that you can get as a proxy for how much energy is in the dark matter, how fast it's moving. And I can tell you that the structures it makes are not that small. It doesn't make things that are the size of a star. It has a cutoff, which is the size of a smallish galaxy or a big galactic bulge. So the smallest it can get is not that small. It doesn't make detailed things.
Okay. So we have a question from Captain Comeback. He's asking, what is the difference between the missing baryons and dark matter? I don't know what the missing baryons are.
The missing baryons are the light that we see, all the particles that we're made of, which are baryons, like the things we're made of, hydrogen, carbon, this stuff, plus neutrinos, photons, normal matter. The amount of normal matter in a galaxy is not all in the form of stars. A lot of it is just floating around, either it's waiting to become stars, and it's just in big nebular clouds, very diffuse, or it's hanging out in the outskirts a bit. And there's different types of it, depending on how it ended up there and how much there is. So we have different names for it, like intergalactic medium, circumgalactic medium, metagalactic medium, interstellar medium, all sorts of things describing how much stuff there is in what looks like the vacuum.
Why was it called missing then, if we know what it is?
Well, I'm getting there.
Okay,
So
sorry.
on average, in our Milky Way, there is 1 atom of hydrogen per cubic meter. So you take a random cubic meter, on average there is 1 atom of hydrogen in that cube. Obviously on Earth it's a lot more. But out there it's much more distributed. And the missing baryons problem is basically that even the stuff that we see that seems to emit some types of light is very hard to find sometimes. So when people started measuring how much normal matter there should be based on gravity, there was some amount missing. And then as we discovered, for example, very, very heated gas that's being pushed out by new stars, that can be shining at different type of light that we don't usually look for. So it's basically building up the inventory of where the normal matter is. What state is it in? Is it in the form of people, the form of stars, nebulae, just floating around? Is it hot? Is it ionized? Is it cold? Where is it? And building that sort of tally. And when you do that, you still miss, I think, about 20% of it. But it depends who you believe, because some parts of it are very hard to see.
And that's not dark matter. I mean, it doesn't fall into the category of dark matter.
No, it's like usually it's very, very hot gas. Very, very hot and ionized gas, because that stuff is hard to detect, so we don't really know how much there is. According to some people, we already have enough of it anyway.
Okay.
So
it's
just
basically
like on the distribution sheet of what baryons do.
Okay, so it's basically a bit less dark matter, because we know it's there. It's just hard to actually find.
It emits light, usually infrared if it's hot, or specific atomic transitions if it's powered by stars and pushed out in between galaxies. A lot of atoms end up pushed out of galaxies because things like stellar winds are actually super powerful. Stars are really efficient at just pushing atoms super fast, and then they fly off into the void. 1 atom per cubic meter might not sound like much, but at the scale of the Milky Way, that's a damn lot of matter.
Yeah, I can understand that. And Captain Comeback is asking another question, considering that, I mean, in regards with the fact that there are issues seeing dark matter, and he also mentions dark energy. Those things, especially dark energy, only happen at very large distances. So he's asking, is it possible that the fact that those things themselves are just artifacts of some sort, that since we have, I assume that it is harder for us to observe things so far away.
Yeah.
I mean, has it been, I mean, I'm going to ask, but I'm sure the answer is yes. Has it been thought about that those could just be errors in detection?
Extensively.
Yeah.
It's been studied extensively. What kind of errors you get, what it could be, also as well as confirming how strong these effects are by completely different methods. That's always the best way in science. You set off to measure the same thing in a completely unrelated way, because now you have to explain why your 2 techniques are wrong in exactly the same amount. That's a bit more difficult. But yes, alternative explanations have been extensively researched. Dark energy specifically has been, first it was supernovae, now it's been seen in many other traces. No matter how you measure expansion speed, you always get about the same number. So it's not great.
Yeah, and yeah, I believe that a few weeks ago someone also asked, I think when we were talking about black holes, if black holes could be responsible for dark matter, because of course black holes are not directly detectable, they don't emit light. So someone said, oh, maybe black holes are very massive, they're very heavy, and they are, for all intents and purposes, invisible. So could that mass be dark matter? And I believe the answer was no. Right?
Yeah, not really. It's true they're invisible, but A, you would need 5 times more black holes than stars. So that's not great.
Yeah.
So you'd notice. And then you have to explain why they appear to be so distributed on large scales bigger than galaxies. Why do all these black holes end up far outside of galaxies while normal stars do not?
Yeah, because black holes are former stars.
As far
So
as we know, yes.
why would there be so many outside of galaxies where stars are supposed to be?
Yes.
Yeah.
Then some people say, well, it's because they were formed very early after the Big Bang. They were formed at the same time as matter, so they've been here since the start. That's why they've ended up out there. And the answer to that is, well, we've looked and we haven't seen them, and we're quite sure that we would have spotted them by now if they really were flying around galaxies in enormous numbers.
Yeah, I mean, 5 stars, 5 times the number of stars seems a bit dangerous as
Even
well.
for elite.
Yeah. So, can you imagine if 5 stars? I mean, every 6 stars, 5 of them are black holes.
I'd personally enjoy that, but that's me.
Yeah, I'm not sure you would, especially if you're looking to scoop some fuel and you're like, shit, another black hole. So, yeah.
Many of us would crash.
Gamer is asking if we can capture the dark energy and use it to power technologies.
Whoa.
I
hope so.
I hope so.
You
too.
hope.
Yeah.
I mean,
That's
in
the
the far
only valid
future.
answer.
In the far future, maybe.
If it comes from the vacuum, then yeah, we could, why not, build ways to harvest it. If that turns out to be the source, just the power of the vacuum, and it just breaks thermodynamics and creates energy out of literally the vacuum.
Power of the vacuum sounds evil for some reason. Are we sure we want to go there? Maybe there are demons on the other side. And
It
stuff like
sounds
that.
evil because it sounds like 0-point energy, which doesn't exist.
Or does it?
Dun dun dun.
Yeah.
No.
I don't know what it is, so I'm going to act as if I know what that is.
Yeah, well, we don't know if it doesn't exist, right? The leading model of inflation is that there used to be a vacuum before, but that vacuum wasn't quite the lowest vacuum. So it collapsed into a better vacuum. And so the universe was born. I've just really stereotyped Higgs inflation there in one sentence. But the idea of the 0-point energy not being optimal is very active in cosmology theory these days.
Okay. Yeah, I don't know. It just sounds a bit weird. Void energy sounds like something out of Warhammer 40k or something. But
It sounds like something out of a scam. Make energy out of literally nothing. Break thermodynamics with this one simple trick.
Scientists hate this.
Yeah,
Stuff like I can see popping it up on Facebook like a few hundred years from now.
Well,
You know.
that's why it's so popular with crackpots.
Right.
As a way to justify selling their favorite free energy device. People fall for that crap. But obviously, if it was a thing, the industry would be all over it. Like, worry not, we are funded by industry. If it was a thing, we'd be building the hell out of it and making money. It's not a thing yet.
Yeah, that is actually one of the easiest way to spot, if a theory is crack or not. I mean, is anyone actually making money out of it? If no, then it means it can't be done. Otherwise, someone would be doing it already.
Or they are all keeping
mean-
it a secret because they're all loyal to each other. Which is
Or
ridiculous.
it's a great investment opportunity.
I mean, yes, it could
Right.
be the Illuminati, but yeah, sure, of course, or the Templars.
But yeah,
Anyway.
energy out of extracting energy from dark energy is far future sci-fi stuff. So why
So,
not?
like, next
Not there.
next week?
100 years? Please fund us.
Right. Well, I don't know. I mean, yeah, if you find a way to harness dark energy, we could pretty much solve energy crisis.
Well, it depends how hard it is to harvest. It's like the problem with fusion. We finally have fusion now, but it's costing more to build the things making fusion than the energy it produces. So it
Yeah,
works.
well, no, we need to
but-
become efficient at it as well.
Yeah, that might take even longer.
Yeah, no, absolutely. We're still trying to optimize our own computer ventilation systems. So, I mean,
Yeah.
so I guess that it will take a while to optimize the harnessing of dark energy.
First, it will be fusion. Then we have to improve even more. But sure.
Or
Yeah,
fusion.
and as every time it is talked about, well, fusion is only 10 to 30 years away. For
yes.
the last
There's-
100 years or so.
Yeah, pretty
There's-
much.
There's a place in France that are building a functioning fusion reactor.
yeah, they are.
Yeah.
France will have
Oh,
one. I
well.
forget what it's called. It has a very cool name.
There's a research a research
Tomahawk?
team there.
Tokamak.
Tokamak,
That's the
that's
one.
it. Yeah.
I think they started out as a research team, figuring out how to, like, I think the one that they were doing research on was the plasma torus one with
Yeah.
the incredible magnetic field, but I think the one they're building is something similar, but I don't think it's oh, I can't remember what it is. I don't think it's
Come on, you can do it.
Try harder.
I think
You want to buy a vowel?
I could, yep, I'm retracting
Okay,
my
let-
statement.
Yeah, just
No, it's true.
just
Sorry,
about it.
I'm not
Let us know
meaning to.
when-
I don't.
let us-
So the one in France is trying to be the first profitable fusion reactor, actually making more energy than it uses. Because the UK has one too. We have the wonderful ITER. That doesn't. It does not put out more energy than it takes in. But the one in France should be, hopefully. So it's finally getting there. It's not quite 20 years in the future. Maybe just 5.
Yeah,
it's-
we'll see.
Well,
I'm pretty sure that
it's pretty much clear that this time we're selling it for real and not just estimating it, because we've got fusion now and it's just a matter of workload to be completed until we actually can use it for profit.
yeah.
Mm.
So we had, I'm just checking if we had other questions. I don't think so. We had surprisingly few questions on this. So if you guys who are listening have additional questions to ask, feel free to.
Take a look at the chat. No.
You
no,
haven't
nothing.
been doing that?
Yeah, I've been looking periodically, but the last 5 minutes I haven't been looking at it. But there have been no questions, so no problem.
Yeah, that's a bit disappointing.
Well,
But,
it's a topic that can't really be answered right now, so I understand why there are so few questions. It's just
No,
a
no, of course.
matter of pure speculation. Haha, matter. See what I did there?
Right, so let's talk about actual, theories that the scientists are, the theories about what dark matter is, or better, what the sources of dark matter could be, and which theories are the most
Right.
researched currently the ones considered most viable to explain this.
Right. So we think, well, we're quite sure that dark matter was created at the same time as the rest of matter after the Big Bang, in the epoch we call nuclear synthesis, where you take the energy left over by the Big Bang and inflation, and that energy turns into matter with E equals mc squared. And it sort of crystallizes out of pure energy into many different types of matter particles. And then over time, these elements combine into molecules and make bigger and bigger stuff. So it was probably made at the same time as the rest. Then what it is, as we mentioned before, probably an extension to particle physics, to particles that don't interact with photons in any way. The leading theories are the sterile neutrino, that's still alive, kind of. Just an extra type of neutrino, you just add it in. It can be produced in huge amounts, and it survives after that. Supersymmetry and string theory both have their versions of what extra particles you add on to the standard model of particle physics. So they have kind of predictions for what the mass of each particle should be, and so on. So it goes back to a question you asked earlier, actually. Could there be dark matter in this room? Well, that depends what the average mass of each dark matter particle is. If dark matter is made of many, many small particles, then it's quite likely that your room is full of them, if they're the size of a neutrino each. But if it's actually made of big and heavy particles, then they're much more sparsely distributed. It's quite unlikely you'd have one. So even though the total mass is known, we don't know how that's split up between the different particle sizes.
Okay. Cool. And I mean, dark energy is even technically more mysterious than that, right? Because it's not even matter. Because when you say it may be an extension of particle physics, it's just because the current model of particle physics, we have always used light one way or another to more or less get a clear picture.
Yes, we only fit in the model what we see. It was that way around. We observe particles, so we build a model to explain it.
Exactly, but that is, in a sense, limiting, right? Because why are we assuming that the only things that exist are interact with light? That's just an assumption.
Yeah, exactly.
So I guess that only now we are thinking, oh, maybe there's stuff that doesn't interact with light. We were so stupid not to think about it before.
Yeah, why should all matter be the kind that we can interact with? That's a bit egocentric.
Exactly. So, but we didn't realize it at the time, right? I mean, at the start we assumed, oh, only things that we can actually see and detect exist. Yeah. Nothing else can possibly exist.
And now we can detect it, but we can't see it with light. So, as far as we know, it exists too. It's just different from what we're used to.
We still have gravity. I mean, gravity seems to be pretty much the answer to everything. Because, it goes back into the beginning of the Big Bang. We still feel its effects. We can use gravity to detect gravitational waves where we couldn't use light to detect those phenomena. So gravity seems to be the next flavor of the month. We're going to use gravity because it's just better than light.
Gravity is the most powerful force.
Yeah, no, but regardless of that, as a way to analyze things, it is more reliable than light.
But remember, the only reason we know how things are gravitationally wrong, like spinning too fast, is because we observe the stars doing the spinning. So we still use actual light to measure it in the end. Without light, there is no astronomy. Astronomy is entirely based on taking pictures. Very, very good, high-quality, distant HD pictures. Yeah. But it's all pictures in the end.
No, okay, I get it, because as humans, we like pictures, okay?
We don't feel gravity. We feel light with our eyes.
Gravity. I mean, if you jump, you feel gravity quite well.
But not very far. You only feel gravity under your bum and your feet. You don't feel gravity in your kitchen over there. you feel gravity of the Earth, but that's it. That's not very accurate. Your eyes are a lot better. We feel photons
No,
very
fine,
well.
but that is simply because we are humans and that's how we evolved. But we have tools like maths and science in general that transcends our human bodies. We use math to describe and explore things that we couldn't possibly experience on our own body. So what I was thinking is, it is true that we use light to see, oh, that galaxy is spinning faster than it should. So we are using both gravity and light. But is it impossible to think that one day we will have such a mastery of the understanding of gravity that we could take quote unquote pictures just by using gravitational data? So we don't see what we're talking about. We only see, I don't know, numbers or however
Enter LIGO.
Yeah, that's what I'm talking about.
We've done it.
Yeah, so you only receive numbers, if you want, data,
Yep.
and then you compile that, if you want, into a picture, but you never take the picture. You just, simulate the
We
picture.
have done that. That is what
Yeah,
LIGO
so-
did. It's absolutely amazing.
Exactly,
But it
so
won't
we
have
don't
any
need
colors.
light.
It won't have colors. That's the
You
difference.
put the colors that you like. If you
In
like
the
green,
end,
you put green. Who cares?
LIGO still works with lasers, and lasers are what? They're light.
Yeah, okay.
There's no getting around it. It's all
No, I mean, no,
humans can really
no,
do.
wait. Don't misunderstand me. We can still use light to build the tools that we require not to use light.
I get
That's
it.
fine. Who
Yeah.
cares? I mean, if we have lasers on Earth, we can use them. What I'm saying is, to detect things far away or things invisible to light, if we have tools like LIGO that can basically ignore light and do everything with gravity only,
Yeah, absolutely.
do you think that's the actual next frontier? I mean, no more telescopes. Just build LIGOs in space and detect everything with gravity.
That's even further away than using dark energy as an energy source. That
Really?
would be far sci-fi, absolutely.
And LIGO in space?
It wouldn't pick up details like, say, a star being born. That's a very small gravitational disturbance, or like a solar flare on the surface of the sun.
But it's still there, it's just too small. But once we...
It is so small at that point that it's sci-fi.
Yeah, no, okay. So even... Okay. I don't know, it sounded like a neat idea.
No, it is. Well, we're going to do better. LIGO only has some specific frequencies it can hear, and with the next generations in space, like LISA, we'll see a lot more detail already than LIGO. But it will not reach the level that we can do light. It will just not. Maybe for a millennium. Humans are so good at using light. It's ridiculous. Their entire lives are based on that one sense.
Yeah, no, of course I'm looking far forward in time. It's just that from what you're telling me, there may be invisible universes that, that light can't really detect. So we need to move past that. We already know that light is not the best mean to well, it is the best for what we can see, quite literally. But we can't just use light. Otherwise, we ignore, what is that, 5 times baryon matter? That we ignore the majority of the universe. We can't see it with light.
Well, let's not be too extreme. We know a lot about dark matter by using its effect on stuff.
Yeah, but it's
So
gravity, right?
Gravity and also the velocities. Ultimately gravity, but we see it with light. Right? Seeing it only with gravity is a bit... Why would you, when you can just use its effect on things we can see? And we should do both, really. We should develop gravitational waves as much as possible.
Yeah, I mean, obviously, I'm not saying light is useless. But, okay, I'm not sure if this is actually correct, because when we talked about dark energy, you said that it is not mass, it is not stuff. But I remember seeing some diagrams somewhere, maybe some talks on YouTube, about some scientist pulling on this pie chart graph.
Yeah.
with the baryonic matter, which was just a very tiny slice. Then you have a way bigger slice of dark matter, and then an even larger one of dark energy.
Yeah. Yeah.
Saying, okay, we only know like 3% of everything that we know is there, we just can't see it because light can only see 3% of stuff.
I think I've seen the same thing. Was it not 5%?
I don't know, 3 or 5, something on those lines, but...
Baryonic matter as a total is 2.2%.
Okay, even worse than that. Okay,
but,
cool.
As I briefly touched on earlier, that's converting this force of dark energy into an energy content. That's why I don't really like calling it energy. It's more of a force. The number we put on it, because that's the way physicists deal with things, we use numbers. The number corresponds to the energy it would take if you were forcing the galaxies apart. That would take this enormous number. I think it's 85%. What's 85 divided by 15?
Don't ask me, you're the scientist.
85.
I have a calculator, give me a minute.
5. So that would take 5 times more pure energy than all the mass in the universe converted into energy. That's how much it would take to tear these galaxies apart. 5 times more than everything else if it turned into pure energy. It's extremely powerful, this repulsion. But it's not stuff.
So this diagram only works if we assume that this force is caused by some sort of invisible mass.
No, it's the energy content.
Yeah, but mass is energy, right? So it's...
Yeah, you can. If you want to compare it to normal matter, you have to convert the mass value into energy value.
That's what I'm
So
saying,
it's
because those diagrams take baryonic matter, which is of course matter, so mass.
Yeah, but they mean the energy content of...
Yeah, no, okay,
matter.
but the converted energy content of matter, okay? Then they take the same thing for dark matter, because we know that dark matter is at least matter, right? It is stuff.
Yeah, and we apply E equals mc squared, energy and mass, same thing.
And then they take dark energy and assume that, and apply the same logic.
Well, no, because that's directly energy.
Yeah, no, okay, but they just skip the step of converting from mass to energy.
It's the amount of energy it would take to pull these galaxies apart. You put a number on it.
But that is a bit dishonest, right? Because it's not energy. It's not the same kind of energy, at least.
It's not energy stored in mass. That's what you mean. It's not energy stored in mass.
Exactly, so it's not stored in mass, but the way, I remember that way that diagram was sold to the public is that we can only see, 2.whatever% of things. So that's not true, because dark energy is not things.
Yeah, it's not things. It's the contents of the universe, but the energy content, not the stuff content.
Yeah. So ultimately you're saying that mass is spicy energy?
Yeah, pretty much. Mass is spicy energy. Mass is energy that got converted from pure to particles in the first moments after the Big Bang, in a big dramatic process called nucleosynthesis.
You see, I'm still at the stage where I'm amateur, and the first thing that came into my head was a universal fart.
Oh, it's gases, I guess.
Yes.
It's more like condensation on a window.
Oh.
It goes from pure vapor floating around to actually condensing into stuff, and the stuff is particles. Energy gets bundled up until it makes massive particles. Then it gets stuck.
Okay, so next time you see those diagrams, now you know.
It's the energy content.
Indeed. Energy content.
Okay.
Any more questions, guys? Because...
well, no.
Because again, this topic is indeed mysterious. I mean, I remember... Well, no, actually, I can't really mention that, right? The secret.
I don't know what you're referring to.
Yeah,
that
right,
secret
you
thing.
don't know.
I often leak things that I'm currently working on.
I
to
know,
you.
and I'm not supposed to know
But
what
I'm
I
not sure
can.
which one you're referring to now.
Everything. We
I
wanna
don't
know
want
everything.
I don't want to get fired, so I don't know if I have the liberty to say it on national radio.
Was
But,
it that time that the
Galactic
theory was
radio.
almost proven? But then it wasn't.
Oh, that time a theory was almost proven, then it wasn't. So most theories ever.
No, you know the one I mean.
Well, the one you mean, I probably know.
The 5 keV emission.
Yeah, I think
I'm
that was
allowed to speak about that.
cool.
The 5 keV emission was the last time that astronomers got their heart rate accelerating because we thought we knew what dark matter was. One of our many experiments to detect it looked like it worked.
So that's the only way to get your heart beat
Oh,
increasing, right?
Yes,
And there are no
it's
other
called.
ways. Literally.
My heart only beats for science.
And nothing else.
No.
Okay.
Cass.
Okay.
Oh. Yes. So we had a big shuffle in the academic community a few years ago, because one of the experiments to detect dark matter had very promising first detections. So what they did was they thought, okay, in some of these models of dark matter, it can emit light. It's just like a neutrino, even more rare. So an exceedingly rare occasion where dark matter would actually interact with itself and make a little blip of light. So what they did was they pointed all their telescopes in the places where we knew by gravity there should be the most dark matter, like the centers of clusters, particularly anomalous galaxies, and those kinds of environments. And we just monitored to see if there was any sort of strange light coming specifically from those locations. For a long time we monitored. And at first, there was a blip. There was a detection at an energy of 5 kilo-electron volts. That's one way of measuring photon energy. Photons of that specific energy seemed to come specifically from those locations. And everyone behind the scenes went crazy. Even though it was not confirmed yet, we were very happy.
Because let's just clarify. If that would have been confirmed, what would that imply?
Because in addition, that energy was one of the predictions of the extra particles of supersymmetry. So in the extensions of GR, combining GR with quantum mechanics, the two leading theories are supersymmetry and string theory. And both of them have ranges of what extra particles they could predict. And that number, 5 keV, was in the range that supersymmetry had predicted.
But not string theory.
Not string theory, supersymmetry. And that would have been both knowing what dark matter was.
It would have killed string theory forever.
And confirming supersymmetry. It would have been the discovery of the century. But then we observed for 10 years more, and it was just a random blip.
Shit.
Yeah, I still feel bad about that. I was very excited at the time. I was talking about it with everyone.
I mean, can't you observe 10 years more just to be safe?
Yeah, no, we are. It's just... It was so hyped. And I think it was a bit overhyped. It was one of these detections that, okay, we see it 3 times, and in both 3 times it's kind of blurry. So like, yeah, let's just observe it for longer, just to be sure. And then it went away.
Well, to be fair, I don't blame you for overhyping it. If that is the only way scientists can get their heart pumping,
Well,
I understand that you want to capitalize on it. It's the only excitement you get in your life, right?
thank you for that.
I know, you said that.
Sometimes I also publish stuff, and I get quite defensive of it.
Right. So, I remember that, I mean...
That was so sad. You've made me sad. I need to get some Baileys.
Yeah. Well, okay. You mentioned string theory. We're not going to talk about string theory or supersymmetry now. I'm not sure how familiar you are with it, but it could be a topic for one of the next episodes.
But I'm not that familiar. I mostly use the applications to astronomy. So the main predictions, like dark energy masses, predictions like cosmic strings and that kind of stuff. The astrophysics aspect. I don't know much about the actual maths that goes into it.
Right, because you can't really observe string theory. So
You can. It makes some very testable predictions.
really, you
Yeah,
can?
it does.
I thought that you would need to observe like 13 dimensions or something.
Well, string theory predicts that in some cases, if you have a string before inflation happens, a string could get inflated at the same time as the rest of the universe, and you'd end up with a string just inflated to the size of a galaxy. And that would mess up gravity where it is, basically.
Right. Okay, yeah, no, we're not getting
that kind
into
of
that.
Stuff.
We're not getting into that, not today. It's a rabbit hole.
But it's testable.
Yeah.
For sure, we are doing it. I mean, I'm personally involved in seeing if fundamental constants change over time, like the speed of light or the quantum mechanical constants. Just testing if they were really the same 13 billion years ago. But that kind of stuff, testable predictions.
Right, and that is actually a secret.
Is
now,
that
right?
testable?
No, I work on it. That's not a secret.
No, I know, but you got some results, right?
That's definitely testable. I can't speak about the results yet.
I know, that's why I'm
I
asking.
look forward to those.
Personally, I know the results, but I can't tell them.
Well, when they get published, please put the link somewhere in the Discord.
For
Yes,
sure.
into announcements.
Yes.
Would be best. And
I believe you that
cosmology, so.
you are one of the authors of the paper, right? You will be one of the authors, the main ones, right?
Yeah, no, it's something I've done and something else I'll still do. I focus on one specific quantum mechanics constant called alpha.
Okay.
But that's probably a different topic.
Alpha.
Yeah, I mean, again, these things, of course, are because the way science works is that you discover something, but you can't just go on Facebook and post about it, right?
Well, you can once it's, peer-reviewed and secure. You don't want to overhype stuff before they're confirmed to be of standards for publication.
So
That
what?
would be irresponsible.
So the results for now are not confirmed.
Well, we're fairly confident. They have to be
Of
reviewed
course
by
you
other
are.
people,
Of course you are. It's your results. You have to be.
But we did the
confident.
best job we could. Then, if they have valid objections, we have to take it into account and change the research. There's often a lot of editing process, redoing stuff based on the comments we get between the time where you submit some results to a paper, then they get back to you, and eventually they agree that it's good enough. Very often you have to up your standards in that process.
Okay. Well,
Which
we'll
is
be-
good, because you don't always notice these things yourself.
So when do you think this result will be public?
Depends.
Well, how? Okay. Like at.
So
Tim?
we're trying for a good journal, and good journals have non-disclosure agreements. So until it's actually printed on physical paper, we cannot discuss it. If the good journal rejects us, then we'll submit it to an average journal, and the average journal doesn't have such a thing. So from the time we submit it to a normal journal, we can talk about it. Because there's no NDA.
Well, come on. From what you told me, I don't see why good journals wouldn't.
Good journals are extremely picky. Good journals like Science and Nature publish basically from all of physics. So it's not enough to be good, you have to be significant to physics as a whole. So
They're not
not only
specialized.
correct, just significant for the general public too. That's why they have NDAs, they have a higher standing.
Okay. Well, sadly, I mean, well, let's not tease our listeners anymore.
Yeah, no.
When the paper will be out, I'm sure it will be on your website. So.
I should do TLDR videos of my current papers.
Ooh.
Why
Yeah.
not? Do that.
That would be fun.
Yeah.
If I ever have a free weekend.
Yeah, because she actually has a YouTube channel, but
Not active enough.
it's a bit barren
I
because
know.
time is a bitch, and it's hard to keep everything.
Anyway.
But anyways, yeah, I was thinking. In addition to that, there was something else that popped up a few weeks ago. You discovered something else, right? Again, I'm not sure if I can.
No, you can. Those are public. So 2 or 3 weeks ago, I had an amazing week when we published, or at least released to the public, 2 papers in the same week. Woohoo!
Oh, not bad. Congratulations.
Yes. One mostly by me and one mostly by my PhD student and me. They were on completely different topics, and those I can talk about because they were not submitted to anything particularly prestigious, just average. And they are online for everyone
Yeah, no,
to
I'm
read.
not sure if that's what I meant. Because Well, we can talk about that if you want, but it was more something about, the largest thing.
Oh no.
No,
You can't.
No.
we can't.
Can we not talk about the
No,
large?
I was trying to, by that, I was, of course, meaning the largest
Sandwich
black,
that I had ever eaten.
Cat, the
Yeah.
largest
Boy.
cat,
Yeah.
currently
I
sitting
didn't
on
have
my
a cat
keyboard.
in my sandwich.
It's just
My joke is
the
poor, I'm
largest
sorry.
the largest telescope ever built. Yeah, it was about that, right?
Give me until July for that one.
Okay. But
We're
it's
going to be in
something.
space for about 20 weeks. That should be fine.
I was trying to get out to you.
I know.
Yeah, she's going to get fired because of me now.
No one listens to this, so it's okay.
No, okay.
Come
Michael,
on.
Michael, you will need to cut this part off.
Oh, come on.
When you
just
upload it.
Move on. It's okay.
When you upload it, just
I
cut
will
it off.
talk about interesting things when I can.
Sure.
I can talk about the things I've actually published.
Yeah. So what about those papers?
We had the most exciting one. It was the first proof that quasars were actually different in the past. So for a long time, actually for the last 12 billion years out of 13.8, quasars have been pretty much copy-paste. You take a black hole of some mass, you throw some matter into it, and what it does with it is always the same. It just depends on how big it is, how much it's eating, and how fast it's spinning. But the actual physics was always the same. They always looked the same. And we have pushed this to the first billion years, past the limit of redshift 7. And back then, and in those very early times, things were different. And it had been suggested for a long time. There were hints, but for the first time we did a big study, doing things properly, looking at all the things that could be biasing our measurement. And we are very confident that they were actually different extremely early on. So that's a cool result.
Okay.
I think it is, anyway.
In what way do you mean they just sort of developed themselves in a different, or well, I was going to say format, but like, or well, I'll let you explain.
Yeah, so basically they have stronger outflows.
Okay.
The amount of stuff, the percentage of stuff that's being accelerated, heated, and ejected with jets, even though it's eating the same amount, it's actually ejecting faster things and more. And we think that might be for some reasons. It could be that the material being eaten has a lot less metals in it, it's a lot more pure, only hydrogen and helium. Although that's not enough to explain the effect we see. It's also because the feeding mechanisms are not in place yet. So black holes usually get fed at later times with a structure surrounding them, what we call the accretion disk, and that's surrounded on a larger scale by a torus. That's like a big donut. It's more like a stack of donuts. Picture a black hole in the middle of a stack of donuts. That's the torus, where the things it's eating are coming from. Then in the very center, there's an accretion disk that's very, very hot, and the accretion disk makes jets that goes through all the donut holes. And that structure, we think, takes time to actually establish. It takes at least 1 billion years on average. You start with a black hole, even if it's eating a lot. At first, it's coming from all directions, and until that structure stabilizes, you have a much more chaotic, much more ejection-heavy regime. So early quasars were even more scary, it turns out.
Well,
Right.
good thing there was no one there to get hurt, I guess.
Maybe
Probably
there
not.
was, but they are not there anymore.
Yeah.
Doctor Who was there when he went back in time.
Yes, exactly.
Did
Maybe
he
he
know
left
about
someone there.
dangers?
I'm sure he knew about all the dangers.
He's the doctor.
Okay. So is she.
Doctor Who had the first FSD boost.
Right.
It's so cool.
Anyway, we have breached, I think, 1 hour and a half.
Yes.
Again, I think we're
Well,
going to
not really.
cut this a bit shorter than usual. Again, we have pretty much explained what dark matter and dark energy is. We have
I've done my
answered.
best.
Yeah, if something is still unclear, you still have a few minutes to answer to ask questions.
Well, yeah. There was one question by Van Otter. I wonder why he didn't ask it on the Discord, because he's on there. I know. He said, I thought the speed of light is not a constant, which is why we tied the length unit to it that it stays constant. I mean, I think he meant so that it stays constant.
The speed of light in a vacuum is constant. People usually omit in a vacuum because it's a mouthful. Speed of light in a vacuum is constant. When it passes through things like air or water, it slows down a bit. That's actually the reason why when you look into water from above, the things you see are at the wrong angle. That's because the speed of light is changing, ultimately.
Refraction?
Yeah, refraction is that effect. It propagates at different speeds in different mediums. And at the interface, when you go from one medium to the other, that difference in speed changes the angle slightly.
Ah.
So the speed of light in the vacuum is constant.
I do hope that answers your question, Van Otter. Otherwise, get on the Discord and explain yourself.
Where did he ask it?
He asked on YouTube.
That's fine.
Yeah.
Oh well, we're there for a reason. So.
Yes. The question is, 6-7 minutes old, so it might have been on another topic, part of the topic.
It's fine. Again, if anyone who is listening in have question, even unrelated to what we're talking about, we can spare a few minutes more.
Yes.
It's okay. I think
fire
our
away.
first
They
our
don't have to
first
be on
few
topic. Sorry, Sarah.
I think our first few shows were a bit shorter, so there's nothing wrong with an hour and a half.
No,
No,
of
not
course
at
there's
all.
nothing
But
wrong. I'm just saying that if someone is limited, because we had quite a few shows, and I can't guarantee that I didn't miss any questions at all. So if someone is listening in and they're grumpy because weeks ago we forgot to ask something,
No, I get them directly too sometimes. It's not.
yeah, no, I'm just asking if guys, people who are listening have other questions. I saw that there was a discussion earlier on Discord about coordinates in space. But
I saw that.
Yeah, I believe that was solved.
was it?
Yeah, the answer is we use something in astronomy called galactic coordinates. Unfortunately, they're not centered on Sage star. They are centered on the sun. But
Because we are selfish and egocentric.
and also, they're completely useless coordinates from an astronomer's point of view. They will not help you find something in the sky, like, ever. And when we go down to telescopes to observe stuff, we need to know coordinates that help us know where to point. Something like galactic coordinates are not helpful, because even where Sage star is changes enormously over the course of the day and over the course of the year. So knowing it's at position 000 does nothing to help you point at it.
Yeah, I believe that we mentioned something. I don't remember what was the actual context. Maybe the CMB, I don't know. But if we could have some fixed point in the universe that we can use as reference point, like for coordinates. Of course, we can't use the sun. We can't even use Sage because Sage moves.
Everything moves.
So,
Yeah.
I guess the CMB.
Couldn't
mean, it
we use
does
the
move,
relative
but-
positions of pulsars? I heard something about that.
Yeah, that should be a very pure way of measuring how fast it is overall expanding. Pulsars are pretty randomly distributed. Oh, sorry, pulsars, not quasars. I got confused. Pulsars.
Yeah, I've seen the question.
For
Okay.
like a galactic positioning system.
Pulsars
like
are
the
good
North
for a
Star.
galactic timekeeping system because they always spin at the same rate, or at least some of them. So no matter where you are in the galaxy, if you could or have on your computer the list of all stable pulsars, you could synchronize your clock using it.
Couldn't
So
you
if
also,
you use your FSD and
if you had the position of like 3 pulsars, or let's say a pulsar grid, that's the term that was used in Star Trek, I believe, like a map of pulsars that you can use to align and compare your locations and maps?
it's useful, but ultimately pulsars are harder to locate than say O stars. O stars you can see from more far away.
Yeah, but
So
aren't
if you're just trying to
pulsars
find your
more
position,
constant? Aren't they more constant? So if you have mapped them, it would be easier?
they're regular in how fast they blink. But O stars don't move around much either. Not
Okay.
more or less, it's pretty similar. Pulsars are good for a timing array, that's for sure.
Also,
Didn't the...
sorry.
Sorry, on you go.
No, I was
Or am I go-
about to change topic.
Oh. Didn't Voyager 1 and 2 on their golden records have the positions of regular pulsars so that we could be located?
Don't remember that, they might have. I honestly don't remember what the Voyager messages were. No, they had some sort of map pointing to us. And they had a map of the main planets in our solar system, including Pluto.
Yeah, we need to go up there and update that. Can we send a patch? Like, we need to patch it.
We need to patch the Voyager records.
Yeah,
'cause they had
as long
Pluto.
as we can, still.
We can't, it's already too late.
Ah, crap.
Actually, no, we could probably catch up to our current
Yeah,
technology.
let's send
but
someone
why
after
would you?
us. Let's just
would
send
take
an
so
engineer
long.
up there to update the Voyager 1 probe and then come back for nothing else.
Voyager,
Let's
yeah,
waste
Voyager
huge
deals.
amounts of money on that.
We're going
I'll
to
do it.
remove content from the Voyager.
Update, removed content.
It's a very expensive DLC to remove content. Yeah, I'm not sure it's worth it.
I wouldn't pay for that.
It's also
Yeah.
not an DLC, it's an ULC.
But
because
can you imagine?
upload
Can
the-
you imagine?
Yeah, it's a
Person to-
ULC.
Can you imagine though? Like, what if the far future aliens actually find Voyager and say, "Look at those retards! They still think that Pluto was a planet. I mean, they're so dumb."
It is pretty strange, isn't it? It would include Pluto, but it's completely missing the other dwarf planets like Ceres. They were like, what? How
Yeah.
did they include that one and not all the other
Yeah,
ones?
these guys are stupid. Let's move on. That's what they're going to think. So maybe updating it is worth it.
Maybe shooting it down would be worth it.
Yeah, God.
That's another thing. On the topic of Pluto, I know it's a bit off of dark energy, but and dark matter. But on the topic of Pluto, I never understood why people got so annoyed by that. Because you just said Ceres, and what about the other ones? Maki, Haumea,
And Eris. Yeah.
Eris, Chaos, or is it Chaos? How do you pronounce it?
I like the name
Eris.
Chaos.
There is Eris, Make, and Ceres.
No, there's other ones even further out, isn't there?
Those ones are the actual spherical ones. I think the dwarf
Ah,
planets, yeah, that's it. Like, they're very comparable to Pluto.
Ah, okay.
Not even smaller. It's just they're just like, why Pluto and not the other three?
For
Only
the
because we
guys
hadn't
watching the
spotted them
stream,
yet.
Sorry, for the guys watching the stream, that was on purpose. Sorry.
Did you crash? Did you do something
I
embarrassing?
face planted in the planet. I kamikaze dive bombed.
No.
But I survived,
Okay.
of course.
Of course you did.
Yeah.
Well, yeah, I think we're going to take one more question from Gamer, and this is going to be a very easy one because he's asking, what is LIGO?
LIGO is a laser interferometer gravitational observatory.
Thank you for the answer. Bye bye. No, I'm joking.
It's currently our only detector of gravitational waves. It's a combination of detectors, 2 in the US, 1 in Europe, and soon 1 in India, I believe. And together they check how much space-time is wiggling when a gravitational wave passes through the Earth.
Wasn't there an attempt to build one in China, but they didn't have the right seismic? What's the word? Seismic.
Stability?
It's essentially that, but it's like seismic isolation. They didn't have the right springs for it or something, and it failed.
I'm not sure that's the reason. I think China pulled out for a variety of reasons. I think they could have made it work. But China scientifically are a bit more closed than the rest of the world.
Maybe they found out about something they didn't want to share with us.
Dun dun
Who
dun.
knows?
Dun dun. Yeah. I
Anyway,
do
I
like
think
me
we
some
discussed.
conspiracy theory.
I think we discussed about LIGO in one of the previous segments. I don't remember which one, but I think we went a bit more in depth about it.
I think it was on the CMB.
Yeah,
Maybe,
that was the one.
maybe.
Because we were talking about black hole and neutron star mergers about then.
Yeah, and what we could see further away than the CMB.
Mhm.
Gravitational waves are one of the main things.
Yeah. So if you guys want to hear more about that, you can just go back and listen to the previous segments.
I think that one is actually still missing. I don't
No,
want
it
to point
was not-
fingers. It's the only one that I could not find on the YouTube channel.
It was the first. It was the very first one.
The introduction, you mean?
no,
no,
the CMB.
Yeah, no, okay, that was number 0. I mean, the first actual numbered episode was the CMB, and the start was missing, I think.
No, I couldn't find the video at all, actually.
No, the video, there was the audio recording.
On YouTube, I could not find it. That's
It's
what I'm
not
saying.
on YouTube then. Well, at least the audio is online on hearthis.at.
Yeah, that's where I found it.
Oh, okay.
There is no
we'll be
video,
sharing
but there
those,
is.
these podcasts on there as well, so people can also subscribe with their whatever podcast playback devices and apps and stuff like that.
Cool.
Because that's
And
all
there
supported
is.
from there.
Yeah, it was one of the first ones, so the audio quality was bad because I still had a very bad microphone, and
Yeah, me too. And
I believe
also
I believe
recording.
that. Yeah, and I believe that you also missed the start.
Yeah, I
think,
might
because
have.
you forgot to start recording. So
But if
Just-
the video stream is available somewhere, someone might have downloaded it. I think Shank might, but he's asleep now, so we can't ask him. Anyway, we can still reconstruct that, and yeah, as I said, the audio recording is available. I can send you the link later.
okay, cool. So yeah, if you just want to refresh your memory about what we talked about previously, just go and listen to the past episodes. We will of course continue doing this as long as people are interested and as long as we have topics to talk about. So if you have any suggestions for next week of something that hasn't been discussed yet, feel free to drop ideas in the channel. Questions, ideas, anything that you want to hear our Commander Shawa talk about, feel free to. And I believe that you're still writing articles for the newsletter, right?
Yes, they're sometimes late, but still at it.
Yeah, as usual, science in the real world can get in the way of elite. So
Cyber science, space science.
This week I've been busy with recruiting too. Well,
You
not
can
even
recruit
doing
me,
science, I'm just
but-
interviewing people, trying to find an extra PhD student to start in October. And it's
And you've been mistaken for a student, right?
3 times so far I've been asked by a student, are you here to be interviewed?
No, I am interviewing you.
I'm
Sit
here to
down.
recruit!
Well, there could be two reasons for that. Either you look just so young, or so stupid.
Oh,
Ooh,
Sorry, I had to pull
both.
that one.
probably
But
both.
I'd say it would obviously be the first one.
Actually,
the former.
it's also because I dress way too casually. So I've tried upping my dress code specifically for this, so it doesn't happen anymore. I went with a jacket today for the first time in like forever.
Can you imagine a jacket?
A jacket.
The
like,
last
what-
time I
usually
wore a
just wear
jacket
broken
was
jeans.
to a funeral.
I know. But yeah, I have to
It's
look
almost
like
the
I'm
thing, isn't
interviewing.
it? The funeral for the
They're
interview.
burying their free time forever. This is the
sometimes you
funeral of having a life.
Sometimes you get students who are older than you.
There's quite a few.
Might be if I become your student, that would be the same. but
Nothing wrong with that. You can go back to science later.
No.
in
I'm
life.
not saying it's wrong. I'm just saying that if you're there to be recruited, and you make the mistake of assuming someone is a student just because of their age, you're not starting with the right foot.
Oh, actually, like funnily enough, they're more bothered by it than me. So when people do that, then they become really awkward and they don't talk to me anymore. Like, I'm still ready to recruit you. I would still like interview you and present you our projects and stuff. But because you made that mistake, now you're too awkward to talk to me.
Right.
I think, given the fact that I'm talking from my personal experience, I think when it comes to people being younger than whoever's interviewing you, a lot of what happens in like primary school and like high school, a lot of the stuff is it's essentially a hierarchy of age, and so that, at least for me, it's just sort of kept on, and so it's still weird for me to not have that at uni, like the idea of I mean, there's nothing wrong with it, but if I was to become a 40-year-old first year at uni, that's strange to me, but it makes complete sense. It's just a previous bias that
It's
I
also
think we
more of a
ha-
thing now.
hold on to.
Yeah. I wish that was more of a thing. It's finally becoming a thing. We're accepting that people can change paths in life a bit more. But yeah, for sure.
Cool. I'm sure you will not, because you're way too dedicated to this.
As long as someone's willing to pay me to do what I like,
But that's
I'm gonna
true.
keep doing
That's-
it.
That. Oh yeah.
won't you
fair.
keep doing it if
I mean-
if you would be getting your money somewhere else?
I'd probably be too tired by my full-time job if my full-time job was something else. I'd still have it as a hobby, but that's not the same.
Well,
But
most people settle down with being paid for something they don't like doing. That they're happy with that.
Yeah, that
Your
makes them
case, I
jealous
guess,
of you.
Yeah, I mean, that's
I hope
luxury,
so.
you know, being paid for something you like doing.
I'm still amazed by that every time I show
Yeah,
up. I'm like,
us
"What, you're
too.
paying me to do this?
You shouldn't
Really?"
be paid at all. You should pay them, right? If you like it.
You know, they're using that logic to pay us as little as possible. You'd still be doing it if I cut your salary in half, right? Because you like it. Salary cut.
That's what I
Yeah.
hate capitalism for.
Yeah, capitalism. Absolutely.
Just put up a cartel or something, or
a union.
a union, a scientist union.
That's
or
a
something.
dirty word.
A federation.
An empire.
Ooh.
Empire doesn't sound that good for PR.
It does not.
It-
The empire of science.
A technocracy or something like that. Anyway, guys, I think we are done for today. We will be thinking about a new topic. As mentioned, let us know if you want to hear something specific. And I believe that is it for tonight. Thank you, Selfish Pie. Thank you, Michael. And of course, thank you, Shoba, for, as always, allowing us to interview you,
Yes.
spreading knowledge.
Yes.
Of course,
Into the black.
thank you to Nightfall for doing this, even though you said you felt like shit.
Yeah, I actually have a cold, and I think I'm starting to feel some lines of fever.
Drink
dear.
more tea.
Oh no.
But hey, tomorrow I have to work, even if I don't like it. Not like this scientist.
I
here
don't like
who-
working when I have a cold. No one does.
Well, let's hope it's just a cold, but you know, it's how it is. Anyway, I'll just go to sleep probably now.
Okay.
Thank you everyone for listening in, and you will hear from us next week.
Yes.
We will leave you with some music now.
Same time, same place.
Right.
Yeah. Jingle at jingle music. That's what's coming
Indeed.
now. Well,
This has been Dangerous Cosmology, Distant Radio 3305.
Yes, let me do some announcements real quick. Well, tomorrow the community goal is supposed to start, but there have been rumors, or at least there has someone been saying that the system will be going into lockdown, which might keep us from doing our community goal thingy. So keep tuned for news on that. Go to FleetCom, have an eye on there. Also, anyway, we will be starting our mining video stream tomorrow. At least that's the plan. And on Saturday, starting at 1 p.m. in-game time, we will have our EDRPG session with Wishblind.
Yes, and I still have to create my character.
Yeah,
And
me too,
I
if I
have no
am
idea
going to
about the
join.
rules, so I am kind of fucked. But hey, I
And
will
of
do
course,
just fine, I guess.
as always, for Friday we will have a talk with Polish Dan and some of the other miners. Even if the community guild won't happen, well, we'll see. But we will keep you posted, of course, our dear audience.
Cool, cool.
Yeah, that's
Coolio
all.
beans.
Have a good night, everyone.
Yes, have
See
a
you
good
next
night.
time.
Yeah.
Bye bye.
Bye bye.
Bye.
Bye.